Hello everyone. In this video, I'm going to derive the consistent mass matrix of a bar element. So to begin with, let me represent a bar. It's a cantilever bar of length L that can be measured in meters, and a cross-sectional area A, and that can be measured in meters square. So these two are the geometric properties. Let me define the material property. This bar is made up of material that has got an Young's modulus value of magnitude E, and that unit is Newton over meter square. Now what I'm going to do is I'm going to consider a small calculus element of length dx at a distance x from the left extreme end. So what I'm going to do is I'm going to take this small calculus element and draw this small calculus element separately, and let me represent the forces that are acting on this small element. At a given time, let us say that the force that is pulling this element on the left hand side is F, and the force that is pulling this element on the right hand side is F plus dF. So the force that is pulling it on the left hand side, it is F, and the force that is pulling it on the right hand side, it is F plus dF. In case if F plus dF is going to be greater than F, then this particular structure should move along the right hand side, because the right hand side is going to be greater than the left hand side force. And also, it's not going to move along the right hand side forever. Of course, the force is going to change in a sinusoidal manner. So the displacement of the mass, if you plot it along the y-axis and time along the x-axis, that should also move in a sinusoidal manner. All right. Now, what is the net force? That is net resultant force, which will be F plus dF difference F, and that should accelerate this particular small object. So that is given by Newton's second law, which is mass times acceleration. So this F and this F, it goes away. So the net force, which is represented by dF, and that should accelerate this small mass. Well, I should not be calling that as m, because it is a small mass. Maybe you may also want to use del m, but I'm just using Newton's second law notations. It's mass times acceleration. Okay, now what I'm going to do is I'm going to multiply and divide by dx. So I'm not going to do any damage to this equation if I simply multiply and divide by dx. That's right. And in the next step, what I'm going to do is I'm going to represent the force in terms of stress. So stress is force by area. So force is stress into area times dx is equal to mass of the object, mass of the small calculus element. That can be represented as density into volume. It's density into A into dx. And acceleration, if u is velocity, then u is displacement, then du by dt is velocity. If du by dt is velocity, then d square u over dt square will be acceleration. So instead of acceleration, I can say it's d square u over dt square. And also in the next step, I'm going to represent the stress in terms of Young's modulus. So Young's modulus is stress over strain. So stress should be Young's modulus into strain, which is du over dx. Strain is change in length divided by original length. So all I'm going to do is plug the value in place of stress, just substitute Young's modulus into strain, where strain is change in length of the small calculus element. So what I mean by change in length, maybe this point is moving along the x direction by an amount u1, and this point is moving along the x direction by an amount u2. So the change in length can be represented as u2 difference u1, which is change in length, divided by original length, this is dx. So it's du over dx. That's right. So that's strain. It's change in length divided by virtue. So in the next step, it is simply d over dx. Instead of stress, you say it's Young's modulus into strain, which is du over dx, into dx is equal to rho times a into d square u over dt square into dx. I can cancel this dx on the right side and dx on the left side. I can also cancel the area. For some reason, I'm just keeping the area as it is. So it's going to be AE. If area is a constant, I can take it outside. Young's modulus is a constant, I can bring it outside the differentiation. It becomes AE into d square u over dx square is equal to rho times a into d square u over dt square. Just I'm going to make one final change, and that is, if this is the force, okay, if this is the acceleration that is taking place in the direction of the force, maybe since I'm representing the force in terms of stress, I can say one is action, the other is reaction. If I treat one to be the action, the other to be the reaction, then those two forces are actually taking place in the opposite direction or in the opposite sense. So I can introduce a negative sign only to mean that the two forces are in opposite sense. So in the final step, I'm going to write the equation. The final equation, it's going to be AE into d square u over dt square plus rho times a into d square u. I'm sorry, I just made a mistake. It's d square u by dx square. That's right. Plus rho a into d squared u over dt square is equal to 0. That's right. So this is the governing differential equation of the longitudinal vibration of a ball. Now, if you are going to assume a trial solution for u and differentiate it 2 times with respect to x and also with respect to t, and if you plug those values here, on the right hand side should be 0. If it is not 0, there is an error, and that is residual. Well, you know all the basics. Now we are going to apply Galerkin's weighted residual method and derive the weak form. So what is Galerkin's weighted residual method saying? Integral of w into r into dx should be equal to 0. That's right. That is Galerkin's weighted residual method statement. So if you have a trial solution, some kind of trial solution that you can assume, and if you just plug it, differentiate it 2 times and plug it here, the right hand side should be equal to 0. If it is not equal to 0, we say that there is a residual error, r. So we know what is r. It's simply the governing differential equation. So in the next step, I'm going to do its integral of w. I should say w suffix I because there can be more than one weighing function, into r, which is ae, into d square u over dx square plus rho a into d square u over dt square into dx, and that should be equal to 0. This is according to Galerkin's weighted residual method. So all I'm going to do is I'm going to take this wi inside the bracket, and let me see what happens. If I take this wi inside, it's wi into ae into d square u over dx square with respect to dx, plus it is integral of wi into rho a into d square u over dt square with respect to dx is equal to 0. Now I have to tell you, I'm not going to do this part. Well, if you want me to do, I can also do that. Maybe, okay, I will do this part, and I will also do this part. I will treat them separately. So the trial solution that I'm going to assume is going to be a linear trial solution. So that's what I'm going to do. If that is the case, let me see what happens now. So the left hand side is integral of wi into ae into d square u over dx square into dx. W is the weighing function. If you have assume a simple trial solution, u of x is equal to a naught plus a1x, you are going to assume a linear trial solution. Because you have considered a small piece, then the deflection, even though if it is a curve, if you take a small piece of the curve, it's a straight line. So that's the reason why we assume a linear trial solution. And the boundary conditions, if you're considering a small piece within the bar, then the boundary conditions are at x is equal to 0, the displacement is u1, at x is equal to L, the displacement is u2. This is at x is equal to 0, and this is at x is equal to L. So these are the boundary conditions. Now, if I just apply this boundary condition at x is equal to 0, then a naught becomes u1. That's right. And if I just substitute at x is equal to L, the value is u2, then u becomes a naught is already u1 plus a1 into L. So that gives me the value of a1 as, okay, u2. This is u2. u2 minus u1 over L. I have got the value of a0 and a1. All I have to do is plug the values of a0 and a1 back in the trial solution. So instead of a0, it's u1, plus instead of a1, it's u2 minus u1 divided by L into x. Now I can arrange the coefficients of u1. It's 1 minus x over L into u1 plus x over L into u2. So these are the coefficients. We call that as the shape functions. You can also call that as weighing functions, because weighing functions are the trial solution with the constants removed. So you can call that as n1, n2 or w1, w2. So this is basically the shape functions. So I can now replace w. I can use n. I can also use w. Both have the same meaning, n suffix I. Now all I'm going to do is I'm going to plug the value of n1 first. But before I do that, what I will do is I'm going to say, I'm going to take this d by dx outside. So I'm going to say it's going to be like d over dx into ae into du over dx with respect to dx. That's right. So this is of the form u dv, integral of u dv. So this is of the form integral of u, where this term is u and this term is d, and this is v. All right, what is integral of u dv? Integral of u dv is equal to uv. Okay, suppose if this is over the limit 0 to L, then uv over the limit 0 to L minus integral of v du. V is ae into du over dx. Okay, that is v into du, which is dni over dx with respect to x. So that is what I will be getting. So in the next step, all I'm going to do is I'm going to substitute in place of u, ni, in place of v, I'm going to substitute a into du over dx. So that's all I'm going to substitute. So in the next step, it is u, which is ni, And what is that v? It's ae into du over dx. It's ae into du over dx over the limit 0 to L minus integral of v du. What is v? It's ae into du over dx, ae into du over dx, v du, into dni over dx, into dni over dx into dx. So, this term is simply the force. Now, how do I say that is force? It's a point load. Now, how do I say that? Because stress is force over area, and the force is stress, which is Young's modulus into strain, stress, which is Young's modulus into strain, into area, and that area can be represented, written here. So force is A into du by dx. I can say it's simply Ni into the force. Maybe I can call that as capital P, the force, the point load, over the limit 0 to L, minus integral over the limit AE into du over dx into dni over dx into dx. Now, if I substitute the upper limit and lower limit, what I will be getting is, I'll be getting Ni at L into capital P at L minus Ni at 0 into capital P at 0 minus integral of AE into du over dx into dni over dx into dx. That's right. Now, we have two shape functions. The first one is n1, which is 1 minus x over L. The second shape function is n2, which is x over L. Now, all I'm going to do is I'm going to put I is equal to 1, which means I'll be putting the first shape function in this equation. Let me see what is the equation that I'm getting. And I'll be putting the second shape function in this equation. Let me see what is the equation that I'm getting. And I'm going to write the two equations in the form of a matrix. That's what I'm going to do. So the first case, let me find out at n, when I put n1, let me find out what is first du over dx. Well, it is simply strain. If you just try to find out what is du over dx in this equation, if you try to differentiate this equation, this particular equation, well, du over dx, well, you simply get u2 minus u1 divided by L. So that's what you are going to get. So if that is the case, then I know what is du over dx. It's u2 minus u1 over L. And when I put n is equal to 1, what is dn1 over dx? Well, dn1 over dx is simply minus 1 over L. And what is dn2 over dx? It is simply 1 over L. Now, the shape function, okay, all I'm going to do is take these values of du over dx, dn over dx, right, and the value of n1 at x is equal to L. Take it and put it back in this equation. Okay, that's what I'm going to do. So let me see what is that I'm going to get. So first case, if I just try to find out what is the shape function at x is equal to L, here we go. When you put x is equal to L here, then it becomes 1, n1 is 1 minus 1, becomes 0. So this term just becomes 0 if I substitute the limits. Then what is the shape function n1 at x is equal to 0? Well, this term becomes 1. becomes 1. So if I use the first equation, all I'm going to get is minus the load at x is equal to 0. So that's what I'm getting. So in the next step, all I will be getting is it's minus the load at 0, at x is equal to 0. It's the point load at x is equal to 0 minus integral of AE into du over dx is simply, I told you it's strain, it's u2 minus u1 by L into dn1 over dx, it's simply minus 1 over L. It's simply minus 1 over L with respect to dx. So in the next step, it's going to be minus the load at x is equal to 0. So if I pull this minus sign outside, so I'll be getting minus of, right? Okay, if I take this minus sign outside, it's going to be minus into minus plus. Again, it's going to be minus. If I interchange these two terms, it's going to be like AE by L into U1 minus U2 divided by L into dx. So if I just integrate this term, I will be getting minus p at x is equal to 0 minus, it's going to be like AE by L square into U1 minus U2. It's see, U1 minus U2. All these terms are constant. I can take it outside the integral. And if I simply integrate dx, I'll be getting x. And if I substitute the upper limit, which is 0 to L, if I simply substitute the upper limit, I'll be getting L. So the expression that I will be getting is minus the load at x is equal to 0 minus AE by L into U1 minus U2. I can call this as equation number 1. Similarly, all I'm going to do is I'm going to substitute I is equal to 2 and I'm going to get equation number 2. So let me substitute I is equal to 2 and let me see what is the equation that I'm going to get. So if I substitute I is equal to 2, then what happens to this shape function here? I will use yellow here, this term, n2 at x is equal to L. n2 at x is equal to L, this time it becomes 1. And what about, so it's just like simply becomes the load 1 into the load at x is equal to L, okay? Minus, what about the shape function when you put x is equal to 0, when n2 at x is equal to 0, this term, again, this becomes 0, so the entire term becomes 0. So that term, I can say it becomes simply the load at x is equal to L, okay? Right, then followed by minus integral of AE into du by dx minus AE is a constant. We know what is du over dx. It's simply u2 minus u1 by L into integral of dn2 over dx. Okay, it's integral of dn2 over dx. What is dn2 over dx? What do you get if you differentiate the second shape function? Second shape function n2 dn2 over dx is simply 1 by L. So you are going to get 1 by L into dx. So this is what you will be getting. So I can write this expression as the load at x is equal to L minus AE over L square into U minus U1 plus U2. All right, and if I simply integrate dx, I'll be getting L for the limit 0 to L. So in the next step, I'll be getting the load at x is equal to L minus AE by L minus U1 plus U2. So this is the equation that I will be getting. Maybe I can call this as equation number 2. So I put the first shape function, I get equation 1. I put the second shape function and I am getting equation number 2. All I'm going to do is write the two equations in the form of a matrix. If I write 1 and 2 in the form of a matrix, it becomes minus the concentrated point load at x is equal to 0. That's a reaction. And the load at concentrated point load at x is equal to L. So that's one matrix minus AE by L. If I write the two in the form of a matrix, the coefficient of U1 in the first equation is 1, the coefficient of U2 in the first equation is -1, the coefficient of U1 in the second equation is -1, the coefficient of U2 in the second equation is 1, followed by U1, U2. So I'm getting the stiffness matrix. If I use the weak form of the Galerkin's weighted residual method, I'm getting the stiffness matrix. For what term I'm getting the stiffness matrix? Well, I'm getting the stiffness matrix for this term. So if I operate the weak form, I get the stiffness matrix as well as I'm getting the load matrix. So in the next case, I'm going to operate this term. I have to operate this term. If I operate for that term, I'll be getting the mass matrix. So I'll be doing the mass matrix. All I have to do is operate on this term, integral of Wi rho a into d squared u by dt squared into dx. So I will write that term separately, and that term is integral of Wi into rho a into d squared u over dt squared with respect to dx. All I have to do is operate this term, use Galerkin's, this is Galerkin's weighted residual method, and let me see whether I'm getting the mass matrix.